Here we have a snowball and it's melting, so that its surface area is decreasing at the rate of 1 centimeter square per minute. We are trying to find out the rate at which the diameter decreases when the diameter is 10 centimeter. So here, let's draw a snowball. Snowball is just like a sphere. You can think about it like a basketball. So at first you have a ball like this, okay? So this is actually a 3D version of the ball, okay? And then it's melting, so after a while, it's going to be smaller and smaller, like this. And we are talking about the surface area. Now let's do some labeling. For this kind of things, we need to know some geometry formula. So in terms of a sphere, we need to know the radius, okay? And then the surface area is going to be denoted with S, and this is equal to 4 pi r squared. So this is the usual formula for the surface area of a sphere. But the problem is, we would like to know this right here. It's at the instance, okay, so let me just spell this out right here. At the instance when, not the radius though, it says the diameter, right? It says the diameter is 10 centimeters. So the label when the D, I will use capital D because later on we are going to do the derivative. I'm not going to use little d. When capital D stands for the diameter, is 10 centimeters. And where's the diameter? Diameter is all the way across, right? Diameter is all the way across from here to here. Likewise from here to here. The rest thing I'm drawing right here is the D. And we know the connection. D, the diameter, is equal to 2 times R. In another word, we can divide both sides by 2. Namely, we know R is equal to distance over 2. And the reason that we do that is so that I can plug in D over 2 into this radius right here, so that I can come with a formula S, which is the surface area, right? But then it will be based on the diameter rather than the radius. So let's see, we will have 4 pi. The R, let me open the parentheses. I'm going to enter D over 2. And then we take this raised to a second power. So you see, now we come with a formula that relates the quantity of the surface area and the diameter. Once again, the question has nothing to do with the radius. That's why we have to go through this little change of variables. Not the radius, but rather we have to use diameter right here, okay? And we can continue. This is just S, which is the surface area, which is 4 pi. And this is the square over 2 square, which is 4. And then we see that this 4 cancels out with that 4. So altogether, we are talking about, let me just write it down right here. The surface area is equal to pi times D to the second power. This is the formula for the surface area of a sphere in terms of diameter. So this is just a quantity equation. Now we are going to take the derivative with respect to time. And as you all know, once the sphere gets smaller, the surface area will become smaller. Likewise, you see the diameter was this long, and now right here the diameter is this long, right? It's shorter. So S is a function of time, so is D. It's also a function of time. When we take the derivative with respect to time, right here, we will get ds dt. And this is going to be, pi is just a constant. We can write it down, no problem with that. And here we have d to the second power. To do the derivative, as usual, we take the power to the front and then minus 1. So we will have, then put the 2 in front of the pi. And then 2 minus 1 is just 1, so we have d to the first power. But then d is a function of time, so we have to multiply by d, capital D, over dt, okay? And this right here represents the rate at which the diameter is changing, dd dt. So this right here is the equation that has the derivative. It's a rate equation. And right here it says ds dt. Well, do we know about that? Yes, we do. Let's go back to the question again. It says that the surface area decreases at the rate of 1 centimeter square per minute. So this right here is telling us that ds dt is equal to decreases because it's getting smaller, and we will have -1. We can ignore the unit for now, but then ds dt is going to be the number -1. So I'm just going to plug in -1 into ds dt, and then the rest. This is just the 2, and the pi is just the pi. And for the capital D, we are talking about the instance when capital D is equal to 10. So I'm going to plug in 10 right here. At the end, the d capital D dt we don't know. So now we can just solve this equation. After we get d dt, then we'll be done. This is -1, and this is 2 times 10, which is 20, and this is the pi d dt. As usual, we can divide both sides by this number, which is 20 pi on both sides, so that this and that cancel. So we can say dt, the rate at which the diameter is decreasing is going to be -1 over 20 pi. And we can just include a unit, which is where we know its diameter. It's a centimeter, so we can put down centimeter per minute. And this is a totally okay way for you guys to answer the question. So you can write down dt is equal to -1 over 20 pi, and then put a unit centimeter per minute. This negative sign is because the diameter is getting smaller. Anyways, that's it.